a little bit of public.
I think you go. Start.
All right. Welcome back. So today I want to discuss dynamic of SUSY breaking with an index and give a couple of examples of that. Before that, though, since I think I have time for that, I want to give a couple of examples about what we talked about yesterday, because I have a feeling that the general theory was probably more confusing than necessary. So let me give you some very specific examples that you can play with yourself. I'm not going to write down the whole solution as simple algebra, really, but just to give you the idea of what kind of situations can arise for certain superpotentials. So let's just take a step back to yesterday. Yesterday we discussed the classical F-term SUSY breaking. Namely, if I give you a superpotential, depending on some kind of fields, we studied all the various conditions for and against the existence of SUSY breaking and the kind of consequences of that. Yes. So now let's just think about a few examples. Suppose I give you a superpotential. So the first thing you do, you want to check for SUSY breaking, right? This is very easy. You just take these equations and see if they have a solution. But I just want to say an important point that you might miss it first. This is including, check also including runaways that might be missed. So for instance, this typical example. Consider W equal to two fields, phi1 and phi2. And let us take as a superpotential this thing here. That's a nice example, simple enough. You look at the solutions, you look at the F terms, and the derivative with respect to phi1 is lambda plus h phi1 phi2, and the derivative with respect to phi2 is h over 2 phi1 squared. Obviously, there is no solution to this set of equations. This sets phi1 to 0, and in lambda being non-zero, there is no solution. So you say, okay, well, there is supersymmetry breaking. Not quite. There is actually a runaway solution. In other words, this, you can come arbitrarily close. You can come arbitrarily close to this solution by taking phi1 equal to epsilon. Epsilon then eventually led to 0. So if I set phi1 equal to epsilon, I can get arbitrarily close to 0 here. And I can solve for phi2 now being minus lambda over h epsilon. So phi2 gets arbitrarily big, phi1 gets arbitrarily small, and you have in the phi1, phi2 complex modular space, well, not a modular space, in the complex space of configuration, you get a runaway solution. So you got to be careful about these things. So this is the caveat that sometimes is missed. Once you have done that, so once you know what your grounds, if you have a supersymmetric solution, or if you have a runaway solution, then you may also want to check for all vacuum, including the ones that do not preserve supersymmetry. So this means checking for solution to this equation, the derivative of the potential. But I remind you that the potential is nothing but the square gradient of the superpotential. Okay? So this is something that we've seen also before, and we've seen that if there is a supersymmetry breaking solution, that is a supersymmetry breaking vacuum, that is something that fulfills this condition but not this condition, then generically you expect a massless particle, and if the superpotential is renormalizable, you expect a whole flat direction of pseudomodules. And that pseudomodules may or may not develop a tachyon, depending on, well, you better check by hand, depending on that funny mass matrix that we probably screwed up yesterday. So, but that's something you have to check as well. So let's see a couple of examples, and then we move on to the new material. So we saw already the Orafferty model, right? The Orafferty model was the model with three fields: phi1, phi2, and x, which was called x because it has the special feature of the pseudo-modules. We have seen that this does not have solutions, SUSY-preserving solutions. We have checked that, if you remember. But we saw that it has a SUSY-breaking vacuum, which is at phi1 equal to phi2 equal to 0, and x can take any complex value. This is the pseudo-model. V is non-zero at that point. V is actually equal to lambda squared, so there is a cosmological term, and there is no supersymmetry preserving vacuum. And you can also check, in this case, check that the modular space, the pseudo, so this is the pseudo-modular space, is stable, vacuum-free, everywhere, OC. You could actually argue that that must be the case, because where else can it go? Suppose, so you can actually show that there is no runaway solution, and there is no SUSY vacuum. There is no runaway solution like this, and there is no supersymmetry preserving vacuum. So if you are at this plateau, at this pseudo-modular space, well, if you develop a vacuum, then the fields must have something to go to, right? If you know that there is nothing to go into, well, that means that the modular space is going to be stable everywhere, right? Just the tiniest modification of this model actually shows you that indeed these two things are related, and things may happen that are present. So here you by knowing that there is no SUSY vacuum and supersymmetry and runaway, you know that the pseudo-modular space is vacuum-free everywhere. Let's make a little modification now and add the tiniest little term here, say a tiniest little mass for, say, phi2. Alright, suppose this is not included in the canonical definition of the Orafferty model, but let's just add it and see what happens. This changes everything, no matter how small the mass is, because, well, it's probably better to just write down now the actual solutions. The actual F term, so this is M phi2 plus Hx phi1 equal to 0. This is the same as before. The one that is modified is the F term for phi2, of course. My phi's are changing between capital phi and small phi at will, and they are indeed exactly the same phi, so sorry about this. So this is equal to M1, the term that you had before, plus this extra correction. And finally, you have the x, which gives you lambda plus h over 2 phi equal to 0. Now you have a solution, because from here, you work out what phi1 is. You put it here, and you work out what phi2 is. And there is a phi2 somewhere here. This is the phi2. So here you work out phi1, here you work out phi2, and here you work out x. Okay? So there is a SUSY vacuum. And it's a SUSY vacuum, so there is now a SUSY vacuum. And it's a SUSY vacuum that lives for mu very, very small compared to m. You see, the solution for phi2 here is equal to minus m over mu phi1. So suppose you fix, so lambda and h are fixed to some value, you find phi1. Then phi2 is, for the, as you let mu goes to 0, you recover the Orafferty model in the sense that the vacuum, the supersymmetry preserving vacuum is pushed to infinity. So if you allow me to write sort of complex number on a real line, so you have roughly speaking, you have a situation like this. If this is phi2 and this is the potential, you have a minimum somewhere here that preserves supersymmetry. where phi 2 takes some value that goes like 1 over mu, okay? And as you let u go to 0, this vacuum is pushed all the way to infinity. So the vacuum can appear and disappear from your model, and you got to be careful that you know what you're doing. So in this case, you know, the theory of supersymmetry preserving. What does it mean for the pseudo-moduli space? This is a very nice exercise that you can do. It actually means that the pseudo-moduli space, which is in a sense unaffected by this term, you can actually check that this solution is still available. It is still a minimum of the potential. It must be because you know, phi 2 equal to 0 is not going to affect this term as well. So this is still a pseudo-moduli space, but now you know that for mu non-zero there is a SUSY vacuum. So what you expect is that now if this is x, is your pseudo-modulus, you expect that now if and this is v, you expect that if you now push x too large, you get into the basin of attraction of this vacuum, and the theory becomes tachyonic, and your potential becomes like this. So these are phi. Okay. So this, of course, these pictures are a little bit schematic because these are complex numbers, but I hope you understand the whole thing. So this is the second thing you want to check, that what the pseudo-moduli looks like, and if they're stable or not against tachyonic deformation, and you're helped by the existence or not of this SUSY vacuum. And the last thing you want to check, if you really want to beat the theory to death, is to compute the Coleman-Weinberg potential. So once you know what the pseudo-modular space is, and once you know what the tachyon-free region is, you may also want to check how the loop collections induced by integrating out the heavy fields generate a mass term, say, for the X field, for the pseudo-modulus. And that gives you, that is given by the super trace of m to the 4th log n squared that we saw yesterday. That's the Coleman-Weinberg superpotential. And it tells you that X, in general, will get a mass, quantum mass, from integrating out the heavy fields. So that will be the third. If you really want to beat the model to that, do the one Coleman-Weinberg, yes, Coleman-Weinberg potential for X. All right. So these are simple examples. I let you play with it. There are some more examples in the notes and in the reviews that I linked on the homepage. But this is the sort of general situation that you can play with if you have a super potential. So now, if there are questions about this, this is a good time to ask. Otherwise, we move to the new subject. Think about it while we're lazy. So we've seen that one way or another, if you want supersymmetry breaking, you need some dimensional parameter in your, say, in your superpotential, right? You're always going to need something of dimension 2 that will give a value to the F terms. Right? Remember that X was always coupled in a supersymmetry. There's always a term like that, right? A term with some coupling constant of dimension 2. Usually it's called F because it gives the F term to this, but just to avoid confusion, I call it lambda. And this essentially implies that the square root of F being the F term for X is non-zero, right? This is what you need, square root just to get the dimension of an energy. This is what you need in order to have F term supersymmetry breaking. This is the very definition of F term supersymmetry breaking. Now the question arises, and this is a question that is motivated by phenomenology, but the answer to this question is very pretty, and it can be appreciated even without any phenomenological interest. But the question is, where does this number come from? In other words, phenomenologically, we would like supersymmetry to be broken at a rather low energy so that we can use it to explain, for instance, the hierarchy between the electroweak scale and and the gas scale or the Planck scale or whatever. So if we are doing it classically, so if we take a superpotential and we put in some lambda, so these numbers must be, say, at the atomic scale. I'm grossly oversimplifying the issue, but basically that's the point. And so the issue is, well, okay, so you need a dimensionful parameter in your Lagrangian that is much, much smaller than what the only parameter that you have in your super gut theory, which is the Planck scale essentially. So why is that thing so small? So that question motivated in the 80s the investigation of whether supersymmetry might actually be broken by very small, tiny effects that are not classically measured. In other words, whether it might happen that you start with a theory, classical theory that is preserving supersymmetry, but quantum corrections violate, so generates terms that violate the supersymmetry. And this is a very, very beautiful thing because then the quantum corrections are in general very small. Not only that, but we have seen that the superpotential, remember that the effective superpotential, we've seen is the superpotential that you take at 3 level, your theory that you start with, then there could be, in principle, a perturbative corrections, but we know that it's not there. We have argued and seen in some examples, and I told you that it's always true, that the perturbation theory, the superpotential is not renormalized in perturbation theory. There are no terms, there is no Taylor expansion in Gilliam-Mills that will generate terms in the superpotential. But we saw that, but we also saw that there can be, and this is the non-perturbative corrections to the superpotential. Now, non-perturbative corrections are, and this is really nice because that means that these guys may be very supersymmetric, and if they do, then the F scale is naturally small without any fuss because it's related to, remember that this one was related to log lambda, this is related to lambda, and lambda is equal to mu e to the minus, but let's do it to all loops, it's dg, let me get the numbers straight. Dg prime in beta g, right? From some initial point that is completely relevant because I cannot solve it in general constant to g mu. Okay, so this is a normalization invariant scale. So d lambda d mu is equal to 0. You can check by the property of the beta function, and it can be naturally, obviously, much smaller than, say, you could put a blank mass here, then this number could be very, very small, so very, very large, and so this guy could be much more smaller than the Planck scale, or the gas scale, or whatever huge scale you want to have in your theory, which your higher theory is quantified. This is the same, if this is lambda QCD, forget supersymmetry, if you think about QCD, and this is lambda QCD, this is why the proton mass is much smaller than the Planck mass, and nobody's worried about it. This explains why the proton, there is no, people don't go around banging their head because the proton is so much lighter than the Planck mass. They know why is that, and we know that because of asymptotic freedom, and the fact that the proton mass is controlled by this non-perturbative object here. The other issue is how to compute it, that's the how to compute the coefficient, but yeah, that's the $1 million question, but it's not answered. So, maybe the same thing happens with supersymmetry. And that was the sort of brainstorm of Witten, essentially, that went and then said, okay, well, this would be great, but does it happen? I mean, how do I know if I have a theory? How do I know if it may happen or not? So Witten introduced an object, which is now called the Witten index, that tells you essentially when this thing cannot happen. And it's the first of a long series of indices that have been created ever since, more and more refined objects that tell you more and more detailed properties about supersymmetric theories or whatever. So, so the issue now is to investigate if we can find some number, some condition that tells us whether this thing can happen. So in other words, that you start off with a theory that does not break supersymmetry, but you generate some non-perturbative potential that makes this whole thing breaks supersymmetry and generates a naturally small F term. Okay? So, to do that, we have to take a couple of technical steps. We have to look at these Q alphas and Q alpha bars. But Q alphas are not well defined in the case of supersymmetry breaking if you take them all over space-time. because of the issue of the zero mode, the zero Costino mode. Q alpha is trying, we saw the explicit expression, is trying to create, it's not mapping one particle state into one particle state, but it's trying to put on to every state it sees in the Fock space, it tries to add a massless fermion at zero momentum. That's usually an undefined, well, that's a non-normalizable state. So in order to make it well defined, we put the Q alphas and the Q alpha bars, everything that we say here, Q alpha and Q alpha bar, we put them in a box. So we introduce a space-time box of volume V, space-time. And we saw that contrary to global symmetry, to usual Pozzolic type global symmetry, you can put things in a box and still have supersymmetry breaking, because you don't have supersymmetry breaking is not related to the existence of more vacuum and whether you can tunnel between one and the other, but it's related to the property of one single vacuum and whether that is zero energy or higher energy. So you can put it in a box and still have supersymmetry breaking. And if you can argue, of course, that if you do not have supersymmetry breaking in a box for any volume of the box, then you will not have supersymmetry breaking if you let the volume go to infinity. The opposite may not necessarily be true. We will see the consequences of this thing. But so once you have done this, and the box better obey periodic boundary conditions so that you preserve supersymmetry. Because if you put some funny boundary conditions on the box, then you break supersymmetry by hand. So we take periodic. So this is a square. This is a square four-dimensional torus over radius L. Okay, periodic DC. Okay. And this then would be the integral over the box, the three-dimensional box of the 3x, the three-dimensional piece of that, of the 3x, of the superparameter, I guess I call it S. Okay? So this is well defined. Good. And so Q bar as well. Now, remember what the most important relations of the whole supersymmetry algebra was this one. Right? Now you put P on the box as well. You put everything in the box. Now from this, if you set, remember the structures of this. For mu equal to 0 and 3, this is diagonal. For mu equal to 1 and 2, this is off diagonal. From here, and P0 here is the energy. So this is a simple algebra to check. If you put 1 and 1 dot here, and you sum with 2 and 2 dot, you get the 4 times the energy. So here you get Q1 dot plus Q2 dot is equal to 4 times P0, which I call the energy. Okay? That's a very simple algebra. All of these objects are positive definite quantities because this is the diagonal of this. So if I take on any state, this object here, Q1 bar, is equal to the norm, is twice, I guess, twice the norm of, well, you pick one of them, that's the same, of Q1 psi squared. So it's a positive or zero quantity. And once again, we see that even in a box, in fact, this is how you should do it, because this makes everything well defined, otherwise this energy is not well defined. You should, so in a box, this is a positive quantity, this is a positive quantity, so this is a positive quantity or zero. And once again, we see that SUSY is broken if and only if this is non-zero. Or equivalently, SUSY is preserved if and only if this is zero. If this is non-zero, then one of these Q's was not an aeronated vacuum, or otherwise they're all zero. Okay? So SUSY is, let's say SUSY is broken if and only if that energy is strictly positive. Alright? Good. Now we want to do better than that. So once you have put a system in a box, you have kind of given up on the whole issue of discussing what particles are, in a sense. The box could be very big, in which case there's still an approximate idea, but really, a particle is an asymptotic state. It's something that you can take and send all the way to infinity. If you put things in a box, the very concept of particle and S matrix become a little bit fuzzy. But that's okay, because you can still define, supercharges, as you did. In fact, you have to put it in a box if you want to define supercharges. And you can also define something that counts. So all you need, we want to have something that tells us whether a state is bosonic or fermionic, without having to worry about whether we can actually identify the particles and go count them. This is easily done in a box by the observation that although the box breaks rotational invariance, obviously. The three-dimensional, the space box, breaks rotational invariance, but not completely. It breaks rotational invariance up to rotations of 90 degrees. This cube can be turned around by 90 degrees on any axis, and it's still a cube. So, although you cannot use the angular momentum operator to measure the spin, spin requires rotational invariance. So, fermions, bosons, you should be able to look at the spin. But you don't have to look at the spin. You can look at this object here, which is the rotation by 90 degrees. I write 90 and not pi over 2 so that you really get the idea that it's by 90 degrees. Is this guy, e to the I, well now I have to write pi over 2 of course, e to the I pi over 2 times say Jz. So Jz is the total angular momentum of whatever state you have. You have a multi-particle state with some very complicated mess in here that I call, for instance, psi here. That thing, J, will act on that thing and will give me something. And this object here is well defined. This is a symmetry of the theory. Not for any alpha, but for pi over 2 is a symmetry of the theory. So remember now that one of the cutest things you learn in elementary quantum mechanics is this thing that fermions don't come back to themselves when you do a rotation by 2 pi, right? I used to do this to my students and they always think it's cute. You do the first rotation, and you're still not quite the way you were before, but then if you do it once again, you come back. So it's actually the same thing. So by taking r to the 4th, which is e to the 2 pi I Jz, this is how you define, this is what will be our fermion number. So we will say that if a state has +1 when I act on it with this object here, then it's a boson. Bosonic state. Bosonic state made of, God knows how many fermions and bosons, but at the end of the day, they will make up a boson. And if it's -1, it's a fermion. Okay? So this object here can also be called as -1. Most of the time I forget to write the 1, it's like minus to the f. Right? So this is -1 to the f. This is how you define the fermion number in a box. These are all sort of technicalities, but I figure that we should probably go through it a little bit in detail so that we don't leave anything sort of somewhat fuzzy, because the issue of defining these objects is somewhat important. And that is why Witten in his original papers have gone through all of this very carefully. I'm just repeating what is written in the papers, in those papers. Good. So why do we need this? We need this because this is going to help us telling us whether this is going to help us discussing whether conditions that are necessary for supersymmetry break. We will see that. So let us observe the following fact first, and we will get to that. Observe the following trivial fact. The Angelantonjian commutes with -f, and the supercharges anti-commute with -f. How do I know? Well, they do because we know that that's what they do when you're not in a box, basically. And this is the only thing that is preserved by the box. And so this is the only piece of the commutation anti-commutation relation that survives the box. So now the fact that minus 1 to the f commutes with the Hamiltonian means that I can take the full Hilbert space of the theory and divide it into eigenstates. It commutes with the Hamiltonian, so there will be a separate an eigenstate of eigenspace of minus 1 to the f equal to plus 1, and an eigenstate of minus 1 to the f equal to minus 1. And this will be the bosonic and fermionic part of the Hilbert space. So let me write the total Hilbert space as a probably a stupid way of writing it, but let me write it like this. The Hilbert space, of course, is a linear space, so there's no bubbles in it. But so let's say that these are the bubbles, these are all the fermions. This is the fermionic Hilbert space, and this is the bosonic Hilbert space, and they don't touch except for the trivial 0, which is not the vacuum. This is just the 0, the origin of the Hilbert space. So they don't touch. So this is 0. This is not the vacuum. So the question is, where is the vacuum? Is it here? Is it here? Or maybe there are more? And first of all, what does it even mean to have a fermionic Hilbert space? Fermionic vacuum. We will answer all of these questions. But one thing we know is that Q maps me, because of this anti-commutation, obviously, if I start with something that is in HF, Q maps me to HB and vice versa. So the Qs and the Q bars, when I write Q, I mean Q and Q bar, they map me from one space to the other, because if I start with something that's obviously, right, if I start with something that is bosonic, by using this condition, I can see that Q alpha is fermionic and vice versa. Which means that here in the HB, I will have a subspace, which is, let me say, the image of HF. It doesn't have to cover the whole thing, but I can take HF, act on all of the states with Q, and then we get something there. Similarly, I can get something here. It's a funny picture that I'm not terribly happy with, but it's already in my notes, so I might as well use it. And I do this, right? And I'm left over with something here, in principle, right? These are the states, these are the bosonic states, for instance, that cannot be written as Q of HF. We can call them primary states. These are bosonic primary states. And these are the fermionic.
But wait, with unbroken supersymmetry, then there is nothing there, or
there is always something there.
there's always something there.
Mm.
So how?
So there, where is there?
Sorry, bosonic primary. So I mean, if we have supersymmetry, somehow we should be able to map any fermion into any boson.
We'll get to that.
Okay.
Actually,
Okay.
yes. So that's exactly the point. That's a crucial issue. Right.
Okay.
So we'll get to that now. I hope ask the question again if you're not happy with the answer. But this is exactly what I'm getting at. So first of all, right. So consider. So suppose there is a primary state. Take a state. Now we will. So I'm starting by assuming something that you have questioned, but we will see that this must be true. Assume that, say, either this space or this space is not empty. So take a primary state. All right, and let us do a little funny table here, and let us see what happens. Let us act on psi with all the Qs. Let's hit it with all we got. We got the Q1, we got the Q2, we got the Q1 bar, and we got the Q2 bar on the side. And let's do it once again. And so we cannot act with Q1 twice, because Q1 twice is 0. Q1 squared is 0. So here we can get, I believe there are 6 states. Might as well write them down. It's overkill because we don't actually need all these details, but just to show you the structure in 4 dimensions, because sometimes the discussion is condensed a little bit, and the risk is that then people are worried that maybe it's complicated to do it directly in 4 dimensions, but it's not. It's just a method. So these are all the states that you can get from psi. By acting with 2 charges. Everything else is a linear combination by using the anti-commutation of the 2 charges and so on. So you cannot have the same charge twice, and 2 of these guys, they don't really commute, but if you commute them, you pick up a p mu. So you get something that is linearly dependent on the other ones. So these are the linearly independent ones. Then you can even get the one with 3 charges. There are 4 of them. 1, 2, 1 bar. 1, 2, 2 bar. I'm being pedantic, unnecessarily pedantic here, but just for fun. So basically, you can only act with 3 charges. So basically, here you have to exclude 1, and then you get the last one, which I will simply write as q to the 4th psi, which is obviously the one where all the 4 charges are there, right? Now, you cannot get more. You cannot get more than 4 charges. You will get 0 or something previously known. So this, by the way, shows you that there must be some primary state. Something must exist that cannot be written as a Q1 or something, because if everything was writable as Q of something, since the Qs are an important thing, at the end of the day they terminate. You could start, so if you say, I have a state, okay, it's not a primary, well, then that means that it's a Q of something. I strip off the Q, then I have another state. Oh, but that's not a primary either. Okay, strip off another Q. You must terminate after the first step. So there must be at least one primary. So this assumption is not, it's certainly true. Question is whether this guy is here, or whatever. Maybe there is 1 here and 1 here. Maybe there is 5 here and 2 here. We don't know that yet. What we know though is that if this guy is a fermion, these 4 guys are bosons, these 6 guys are fermions, these 4 guys are bosons, and these guys are fermion again. And vice versa, these guys are bosons, blah, blah, blah. So, in general, out of this table, you get, what is it now, 8 bosons and 8 fermions, regardless of the nature of this guy here. Right? So here you will get, so from this table, you will get 8 fermions, yeah, I'll say it once, 8 fermions and 8 bosons. Suppose now that this psi actually obeys some extra condition. For instance, let me write it here. So for generic psi, by acting on it with the Q's and so on, I get 8 fermions and 8 bosons. 8, right? Now suppose Q is annihilated by one linear combination of supercharges. Suppose Q1 on psi is 0. This is a condition that you may want to have, but not the others. Okay? So what do? Well, then I have to drop, let's see if I can get this right. Then I have to drop all the terms that contain a Q1. And now I get how many fermions and how many bosons. I get, say, if this is a fermion, there is 1, 2, 3, 4 fermions, and 1, 2, 3, 4 bosons. And vice versa, if this is a boson. So if one of them is 0, I have 4 fermions and 4 bosons. If 2 of them are 0, say Q1 and Q2, check this, it doesn't matter. Q1 and Q2 equal to 0. Then I have to kill the Q2 as well. So Q2, I kill this one, I kill this one. Oh, sorry, this one is killed as well, of course. And I kill this one as well. And I have 1 of the same statistics, say 1 fermion, 2 fermions, and 2 bosons. So vice versa, 2 bosons and 2 fermions. So 2 fermions plus 2 bosons. Suppose I have 3 of them. Q1 psi, Q2 of psi, equal to Q3 of psi, or well, Q1 dot of psi equal to 0. And then I don't really have much left. Here everything goes away, here it goes away, but I still have 1 object here and 1 object here. I still have 1 boson, 1 fermion. 1 boson plus 1 fermion. The last case is where all Q's on psi give 0. Then I have only one guy, one single thing, psi. That can be a fermion or a boson. Psi is the only thing that survives. And so it's 1, and I don't know whether it's a fermion or a boson, but it's 1. So the big difference between all of these guys and this case, which is the vacuum, of course, if there is a psi that annihilates all the Q's, it's the vacuum. It's the SUSY-conserving vacuum. That's the definition of the SUSY-conserving vacuum. It has 0 energy, kills all the supercharges. The energy is positive, so that thing must be the lowest state. We're in a box, no problems with the regularization or anything. So that thing is the vacuum. If this thing exists, if there are such terms, there could be more than one, but if they are unpaired. I don't know if they are fermions or bosons, but they are unpaired. All the other ones, they're always paired. So if I start out, if they were fermions, I would get a boson and so on and so forth. The bottom line is that so the sum of this is 8, which is even, the sum of this is 4, which is even, the sum of this is 2, which is even, and this is 1, which is odd. Okay? So that's where the nature of the index comes about. If I now manage to sum up all the states, so if I now take the following note, which is the Buchan index. Consider, so this system is in a box, so we can think of it as a very big generalized quantum mechanical system. The Hamiltonian is the Hamiltonian, it's well defined, it's in a box and so on. Suppose I consider the sum over all states in H. In H is both HF plus HB, in all states of this thing here. Which I can write, of course, as the trace of minus 1 to the f and e to the minus beta of h. Beta is a number. It's called beta because you could think of this if this is a partition function. This could be the inverse of the temperature, but it's a number. And h is the Hamiltonian of the system. Now, what do these things? What happened to this thing? So. By the way, this can also be written, now you have seen what the supertrace is, and this is nothing but the supertrace of e to the minus beta h. You can also write it this way. This is the definition of the supertrace is that it's a trace that you take a minus sign if you're doing it over a Fermi state. So what happens now if you do these things? So you see, all of the states are all of the states that we have constructed here, here, and here, the bosonic and the fermionic states, they have the same energy because we have seen that the Hamiltonian commutes with the supercharges, so they have the same energies. So this picks up the energy. So you see, if the only thing that is unpaired are the ones that have 0 energy. So all of these guys have positive energies. Because some of the supercharges are not do not annihilate the Q's, the psi, so the energy cannot be 0. This guy is the only one that is annihilated by all the Q's, so it's 0 energy. These guys are positive energy, and they're paired in positive and negative, in fermions and bosons. So, they will not contribute to this trace. Because, this guy here is basically just a regularization object. Eventually you add this index without even bothering with this. But these things here, they will not contribute because every time I have a term, a psi, that has a positive energy, that gives me a certain term, there will be an equal number of psi's, which with an opposite fermionic number that cancel this sum in the trace. So the bottom line is that the only thing you get is that the trace of -1 to the f to e to the minus beta dh must be equal to the number of bosonic vacua, meaning the number of size of this type that belong here, no, this is fermionic, okay, well, this is fermionic vacuums, and this is the bosonic ones. Okay. So the number of bosonic vacuum, meaning the number of size that are inherited by all the four supercharges that are 0 and that belong here, minus the number of fermionic. All the other ones cancel. Right? So this e to the minus beta h is actually, so it's in particular, this object here is independent of beta. Because the only thing that depends on beta are the contribution for the states that have a non-zero energy. But that contribution overall cancels. So this thing is independent of beta. This is a clever way of arguing that. So in some cases, it's very interesting. You can actually compute this index by forgetting for a moment that this thing does not depend on beta and trying to do a computation where beta is very large, so you can do perturbation theory, because this now is very small. And what you get is something that actually will not depend on beta. Okay, so this is a nice, clever trick. But instead of, so we will see concrete examples of that. But now what have we learned now? So now we can actually say the following statement. Remember that Susie is broken if and so suppose this number is non-zero. Suppose this number is non-zero. Suppose I have magically managed to compute this number and I find it to be non-zero. What can I say? Well, if I find it to be non-zero, that means that there must be some vacuum, either in F or B, I don't know where, but some vacuum, either in F or in B, that has zero energy. So, this is called, okay, I should say, this is called the Witten index. It's usually, we can just write it as trace to the minus of the F because it's independent of beta. And if this is non-zero, then Susie is unbroken. This is the only thing you can conclude. Why can't you conclude that this is also true? Well, if Susie is unbroken, then you know that there must be some vacuum. That one of these two numbers must be zero, must be non-zero, because there is a zero energy vacuum, zero energy state. But there could be one here, or two here, and two here. And so this does not follow directly. Okay, so this is a typical property of the index. It tells you something, it doesn't tell you everything. It tells you usually. So this is or better yet, a necessary condition for Susie to be broken is that the Witten index vanishes. So you turn this around. Okay, you can play with the logical implication of the issue. Now, it's almost time to take a break, I think. But so if the Witten, so let me say a few words and then we take a break. Is it clear so far? I mean, is this is if anything of this lecture should be remembered, is this thing here, right? But of course, the usefulness of this object depends on two things at least. One is whether you can actually compute it. Because if you can't compute it, well, right. And two is whether this object here is actually something generic that you can say about the theory and does not depend on perhaps some very specific details of the theory. And this is actually, in both cases, the answer is true, is yes. The Witten index is both computable in many interesting cases, and it's and this is what we will argue a little bit after the break. I think we can take it right now. Is that it is stable. So what we will try to argue is actually very simple. You can draw like a sort of a picture. You can prove is by drawing basically. It is stable under a certain large class of modifications of your theory. When I say modification of a theory, I mean I have an ultraviolet theory, but I take the MSSN or something. Take a supersymmetric theory of your liking. And this theory is given by a bunch of parameters, the coupling constants and the masses and some extra terms in the superpotentials, right? It would be a bummer if this index here turned out to be a complicated function of all of these things, because well, that would make life difficult. It turns out, in fact, that this thing is remarkably stable against changes in the parameters of your theory, but not entirely stable. There is an exception, and this is what we will discuss after the break, because it's an important thing. This thing is stable under all the deformations of the theory that do not alter the behavior of the potential at infinity in field space. This is something we already seen. We have seen with the F-terms example, the simple example that I did at the very beginning of this lecture. We have seen that in some cases there are some vacua that can go in and out from infinity. Okay, we have seen that you have a SUSY breaking state, but then if you add a little mass term, all of a sudden you have a very, very far away in field space, you might get a SUSY vacuum. And if you let the mass go to zero, then that SUSY vacuum goes to infinity. These are the kind of things, and these are the only kind of things that change the Witten index. Because the Witten index counts the number of these vacua, and we've already seen that in some cases the number of these vacua changes discontinuously, because if the parameters in the superpotential is some parameter is set to zero, then all of a sudden one of these vacua disappears off to infinity. So in that case, and only in that case, you can have a discontinuity in the Witten index. So we will put this a little bit more flesh into these statements, and see a few examples, and discuss maybe a couple of examples of true dynamical supersymmetry breaking. But that could happen. Take a look. There was a question before during the break. There was a question during the break on what is a fermionic ground state, and because usually we think of bosonic ground state, fermionic ground states. On the other hand, you all string theories. You all know you've taken an elementary course on string theory, so you know fermionic ground states very well. Think about the Ramond ground state of string theory. It's a state which carries a representation. You know, when you quantize the fermions in the Bushmaster-Ramond formulation, if you put Ramond boundary conditions, you have zero modes. This creation and annihilation operators for the fermions have zero modes. They should behave like Dirac matrices, and you are forced to assume that your vacuum carries a representation of these things. That's a fermionic state. That's a fermionic state. So, and generalization has nothing to do with string theory. You can do it in any theory. If you have a fermionic zero mode, there will be some representation carried by the vacuum. That's a fermionic state. Right. So there is a very mild. So before I go and discuss pictorially really the why the Witten index is stable under this deformation, let me just say that there is a mild generalization of the Witten index, which is useful sometimes. I mean, it's so trivial that I will not really dwell on it. Suppose I have an operator O that commutes with all the supercharges of symmetry to zero. Okay. Then you could just take the Witten index on the state. So if it commutes with the supercharges, it also commutes with the Hamiltonian. And so you can actually study the projection of the whole Hilbert space on some eigenstates of this O. And if you find that the Witten index in one of these spaces, in one of these points, in one of these subspaces is non-zero, then you have found a vacuum, supersymmetric vacuum. So you can actually, instead of just using the Witten index, you can put any operator O that commutes with the Hamiltonian. Usually they're discrete operator like charge conjugation and so on. This is, by the way, how you prove that that supersymmetry is not broken in super QED. In super QED, the trace of -1 to the F is 0, but there is an operator which is really charge conjugation whereby where you can actually show that that is non-zero. So as long as one O exists, could be 1, in this case you get back to the usual Witten index. As long as for any O that commutes with the Hamiltonian, if any of these things is non-zero, then SUS is not broken. Is non-broken, yes. SUS is not broken. My generalization that may be useful for some cases. So let us then go back to the usual Witten index, the one that just takes -1 to the F. And so the usefulness of this object, of course, is due to the fact that it can be computed and it's stable under many deformations of your theory. Stability is actually, it's kind of intuitively obvious, and I will stick at that level. It can be made as precise as you wish, but really there is not much more to add than just draw a picture of all the possible energy eigenstates of your system. We're in a box, so the energy spectrum is discrete. In a box, the energy spectrum is discrete, and there will be a bunch of states, multi-particle states, but there are no particles. I mean, all of your messy Hilbert space will fit some huge spectrum here of energies, and then there may or may not be states at zero energy. So let's say that these are the fermionic ones and these are the bosonic ones. You know that if the energy is positive, strictly positive, then the states are paired. So you could have 4 here, you could have 2 here, you could have 8 here, and so on. They're paired. Here they could be unpaired. There could be 1 here and 3 here. That's the only case. Now, so this is the spectrum, and this spectrum will depend on a bunch of parameters, the coupling constants and the masses of your theory. Now, so each of these levels, epsilon, will depend on all the coupling constants of your theories, the masses, and all of these things. What happens if you vary them? Well, if you vary them continuously, then these numbers will vary continuously. And, well, these numbers will just, these lines here just move around like you do in the spectrum. You turn on a magnetic field in the hydrogen atom, that's what you see, right? You see the spectrum that changes. That's exactly what you do. You're in a box, it's a quantum mechanical system. So it might happen that, that you turn on some fields in such a way that one of these states, pick this one, well, pick the lowest one, goes to 0. So suppose you are just in a case where, so you have your 3 states here, and then all of a sudden this guy, for some values of these fields, point touches 0. Well, then all of a sudden here you have 4 more states, and here you have 4 more states. With an index hasn't changed, right? Similarly, you could even have some of these vacua being lifting up. So you could, for instance, for some values of the coupling constant and the masses, you could have that some of these vacua are no longer vacua. Then they would move up in the spectrum. But if they move up, they have to move up in pairs. So if one of these guys, say this guy moves up, then there must be one of these guys, say this one, that moves up as well. So you will get an extra line here with one of your old fermionic states. But now you have 1 and 3, now you have 0 and 2. With an index hasn't changed. Right? So any deformation of the theory that does this thing, that mildly changes the spectrum, does not change the Witten index. That's just as simple as that. But there are deformations, we already seen some, that actually just go and kill some of these things. In other words, they take some of these states and push them out at infinity. What infinity if I'm in a box? Infinity in field space, not in space-time. Infinity in the configuration, there is some field which can take a maximum expectation value. That thing isn't in a box. That thing will go to infinity. And if that thing goes to infinity, if some of these guys is characterized by the depth of a field, or a composite field, or something that can be brought to infinity with some change of parameters, then that might make the Witten index jump. So, quantum mechanical example of not jumping Witten index. Remember what we've seen. So if W, if W had an even number of if W has an even number of zeros, the Witten index doesn't change. So what is the Witten index for this theory? This is X. Remember the quantum mechanical example. What is the Witten index for this guy? You should know, because first of all ask yourself the question, is supersymmetry broken here? Yes, because V, remember that V is W squared. Supersymmetry is broken in these cases. So the Witten index is, you don't have to compute it. You know that it must be 0. Because if it was not 0, so what happens here? Here you have one, so here you can deform this thing to this thing just by lifting it up without changing the boundary conditions here. So these two vacua here, they don't go to infinity. They pop up of existence, but in a limited interval. So you take this parabola, say, and start changing the parameters in the theory until the parabola is lowered down. The parabola is lowered down, and all of a sudden you have two vacua appearing here, and they open up, and here they are. Or you can make a messier thing, but all of these things are bounded. They are staying here. You are not changing the potential at infinity. Witten index doesn't change. How about we take our parabola, and now we actually take this thing and lower it down like this. All of a sudden, when this thing touches the axis at infinity, a new vacuum appears at infinity and comes in from infinity, like this, for instance. Okay? Here I am changing the boundary conditions at infinity, and I am bringing in a 0 from infinity. This 0, that let me draw it explicitly here. This 0 here, which is at large x, it has to be at large x. Cannot be. The difference between this 0 and this 0 is that all of these zeros are within limits, so they don't change. So whatever you count is bound to be obeying, sort of giving the same Witten index. Here you're bringing in a new guy from infinity by changing the boundary conditions, and so the Witten index goes from 0 to 1, and supersymmetry is restored.
So how do we know that Witten index doesn't change there? It could be that you're forming two bosonic vacua.
You know because of this.
Ah, okay, because you're just moving that.
Or you can, if you're a hardworking dude, you can compute it and one is from the other. This is the argument for that. Okay, so that's it. So that's the stability of the Witten index. Now, so since we are doing field theory, I cannot help but giving the simplest. I cannot help by giving the simplest field theory example, which is really that thing there, but in field space. So field theory example is W equal to M phi squared plus G phi cubed. So this is not an example of supersymmetry being broken or unbroken. Supersymmetry is always unbroken, but the Witten index will jump. So here, this is an interesting point. So So what is the Witten index of this theory? So Vesuvino model with one chiral superfield. What is the Witten index of this model? Well, let us look at the solution for this. Solution for this are, so this is 2m phi plus 3g phi squared equal to 0, so it has two solutions, phi equal to 0 and phi equal to minus m over g. There are two classical vacua. So there are two vacua. I claim this is, in this case, you can actually argue immediately that these are both bosonic. So in this case, the Witten index is 2. Why do I know they're bosonic? Because if they were fermionic, there should be, if there is a fermionic ground state, there must be a fermionic zero bond. There are none here. As long as the mass is non-zero, all the fermions are massive. So there cannot be a fermionic zero bond. So there are two vacua and they're both bosonic. Okay, so that's another statement that you can make when you compute the Witten index. Even if the Witten index is 0, no, I couldn't say. Yeah, if the Witten index is 0 and you know that there is a vacuum, you're not in a runaway thing, then there must be, if there is a vacuum, then there must be another one. So if the Witten index is 0 and you know there is a vacuum, a Susy-Perserving vacuum, then you know there must be at least one fermionic Susy-Perserving vacuum. But that can only exist if there is a massless fermion, because that's how you construct it. So if you know that there are no massless fermions in your theory, you know that there cannot be a fermionic vacuum. So if you find a vacuum, it's got to be bosonic. So it's very simple if you think about it. So this is a case of Witten index 2. We know supersymmetry is not broken, of course, and that's perfectly consistent with the fact that Witten index 2. In fact, we use the fact that supersymmetry is not broken to compute the Witten index. The importance of the Witten index is to go the other way around, of course. This is a trivial statement of something we did before. But suppose now we set G, so we let G go to 0. So what does the potential look like? So the potential here, which is m5 plus g5 squared, right? So the potential as a 0 at 0, and the 0 somewhere at minus m over g. Right? So and these are my two ground states. Do not confuse this with the example of quantum mechanics, where this guy here, for instance, was giving a similar potential, but supersymmetry was actually broken. I leave it to you to see why this is a different case. But in this case, however, we still have this going off to infinity when g goes to 0. So the Witten index changes, and of course when g goes to 0, I have a parabola, and the Witten index at g equal to 0, the Witten index is plus 1. It has jumped from 2 to 1 because this guy's gone off to infinity. This is consistent with the fact that if I set g to 0, the superpotential change, or the potential, say, changes its asymptotic behavior. So something can have come in or gone out from infinity. So this potential goes like phi to the 4th for g non-zero, but phi squared for g equal to 0. So this is a dangerous case where the Witten index might change, and in fact it does. So okay, this is a silly example in a sense, because it's an example of discontinuity, but it's not an example of a computation of the Witten index, because we use the knowledge of the theory to derive what the Witten index is. It's much better if you have a theory where you don't know whether supersymmetry is broken or not, and you would like to find out by computing the Witten index. And there is one colossal class of theories that in fact was established by Witten itself in the paper, where you can compute the Witten index, and that is the only way you can argue basically that there must be that you show that is non-zero, and that means that these theories will never break supersymmetry. And this colossal class, well, it starts out with the fact that, and this is a theorem that I will not prove because the proof is a technicality. It's really a technical proof about being very careful with the boundary conditions and so on. It doesn't give much to give the proof to the table at the blackboard. You can read it in the original paper. For a pure gauge theory, pure Young Mills, so no chiral field, just matter, just gauge bosons and gauginos, based on gauge group G, SUN, E6, whatever it is. The Witten index is half of the index of the job. Sometimes also called H, the dual toxical number. In particular, for any simple group, this object is non-zero. This means that SUSY is unbroken. The proof of this fact is, I refer to you to the original literature. It's a technical proof. It's not difficult, but it requires careful. It requires being careful, and I better not do it at the back. So, in particular, now that you, for instance, if you have a symmetric gauge theory, you already know that's something that happens in QCD, namely the existence of a dual condensate. In QCD, there's some rules that allow us to compute the masses of the mesons and so on by putting in some phenomenological expectation values for the condensate at work, and they quote the chiral condensate and the dual condensate. These things in general are non-zero for QCD, but this must be zero in super QCD, for instance. Must be, because if it wasn't, it would break supersymmetry. But SUSY is unbroken because the Witten index is non-zero. On the other hand, this guy here, the trace of the Bruino condensate, can be non-zero. It's just a color variant of this thing. What this can be, may or may not, it is in general. Because a condensate like this does not break SUSY, we saw it. It's not a variation of something. It's not so, but it's okay. It's not an F term. Right? So you can just you can actually say something very deep about the infrared dynamics of the theory just by computing this topological object. You have proven, for instance, that this is zero. So this is a colossal example because it applies to all pure gauge theories, but it also applies, just with one extra step of imagination, to all gauge theories for which you can give a mass to all the chiral fields. For which all the chiral fields have been given a mass. Now, you know very well that they are called chiral because in general you cannot give them a mass. Because if they transform under a non-real or pseudo-real representation of the gauge group, you cannot give them a mass. This is exactly the same thing that happens in the standard model, where you cannot give a mass to the quarks and the leptons because they do not transform in the same representation of the gauge group. So if we say that the theory, it's a bit of a, maybe it's confusing more than first, but it's so common in the use that you may know this. We say that the gauge theory is vector-like if all the matter fields can be given a mass, meaning that the representation of these vector-like fields that may or may not be reducible, could even be reducible, but is still such that it's equal to its complex conjugate. So there is an invariant binomial. There is a mass that you can write down. If this is not the case, then we say that the theory is chiral. Okay, so vector-like theories are theories where all the superfields can be given a mass, and otherwise, if the representation of the gauge group is not self-dual, real or pseudo-real, then the theory is called chiral. So if you can and do give a mass to all the vector superfields, so suppose you have, so this thing here immediately generalizes to the case where you have a vector-like theory, so a theory where you can give a mass to all those fields, and you do give a mass to all the fields. So if you have a theory like super QCD, so take super QCD. Super QCD does not break supersymmetry. But there is an important caveat that I have to mention because at this point, since there's been an extremely popular and studied in the last decade. So, super QCD, which is after all a gauge theory with gauge U plus UN, with a superpotential W of this type, does not, so has, let's say it this way, has a SUSY vacuum, at least one. How do I know? Because I apply exactly the Witten index argument. I say, if M is very large, so this is a super QCD is a vector light theory because my Q tilde can be paired up into a mass term. No massless fields are left. So if I take the mass and I put it to infinity, and if I send it off to much, much higher values than the energy scale that I'm studying, I get back pure Young Mills. Now, I can lower this mass without changing the boundary condition as long as I stay away from zero. As long as I stay away from zero, no matter how small this mass is, the boundary conditions of the potential will be the same. So for any mass non-zero, the Witten index is the same as the number of is the same as half of the trace joint, which in this case is MC. So if you do give a mass to all of the fields, and you can do this only for the vector light theories, then the theories will not break supersymmetry. There is a caveat to this, which is crucial and which is important for even for terminological application that I have to say now, and then we will see then that there are only two ways out if you want to find theories that break supersymmetry. The caveat is the following: this theory does actually have metastable SUSY breaking, of course, vacuum. This has been proven by Interligato Cyber and Shi, 10 years ago, and it is based on the fact that we went a little bit fast on this one when we discussed dualities of n equal to 1 theories. But for a certain number, I will not go through this because I want to end in 15 minutes. I want to talk about something else. If you're interested, we can talk about it. It's a very well-studied example. There are some cases, in particular, the case that we haven't really discussed much is the case where, if you remember, NF was large. So NF was still within the asymptotically free region, but it was larger than NC plus 1, so larger or equal than NC plus 2. Right? In this region, we saw that there was a window here between 3 and 3/2 NC where the theory was actually conformal and dual to a conformal field theory. In general, however, this duality works in all of this region, and for an F small enough, you actually flow to an infrared theory, this dual to the one that you started with, and that infrared theory that becomes weakly coupled, as this theory becomes strongly coupled, that infrared theory is essentially a generalized O'Lafferty model, and you can just look at the classical potential and see that it breaks supersymmetry. So this doesn't prove that there is a metastable vacuum. You have to do a lot of work to show that that vacuum is actually stable. So you have to compute the Coulomb-Weinberg potential, essentially, and make sure that you don't get vacuums. And remarkably, it actually does work. So you do end up with a very concrete and calculable example of the metastable supersymmetry breaking at strong coupling. So it is true that the Witten index is non-zero. It is true that this theory does not break supersymmetry, but this theory is used in supersymmetry breaking model building because there is a metastable vacuum. Then you may want to check that that vacuum actually lives longer than the age of the universe, otherwise it will not be very interesting. I will not discuss that, but instead I will conclude on another issue. So we saw that. So suppose we want. So far we've seen theories that break supersymmetry classically. We've seen theories that do not break supersymmetry quantum mechanically, dynamically, like super QCD. Now it would really be nice to find a theory which we haven't seen yet. It would be nice to find a theory that breaks supersymmetry dynamically. That's the whole point of the Witten index, right? So, but being the Witten index so strong and so stable against the deformation, we have two ways out. So to find to find a theory, gauge theory, that breaks Susie dynamically. But certainly we need some massless chiral fields, because otherwise we have just proven that this thing is not going to work. We need massless chiral fields. So there are two options. Either we take a chiral theory. So we have to look at chiral theories. Chiral theories, like the standard model of the MSSM, for instance. The MSSM does not work supersymmetric as you want, dynamic as you want. But the chiral theories are theories for which you cannot construct a mass term for all the fields. So this thing does not fall in this category, and the Witten index for these theories is it's a tricky issue. And certainly you cannot argue that it's non-zero. So this calculation fails in this case because you always have to work with some massless fields. Or you can take a vector-like theory, but with some masses set to 0 by hand, and that change that violate that change the behavior of V. That is, they change the boundary condition of the potential, just as we saw in the examples so far. So that could bring in or out some vacuum that makes things work. There are two prototypical examples of this. This one, the first theory of this type, I believe, was again due to Affleck and Seiberg. It's work that was done shortly after the Witten index, and this one took a little bit longer. But then there are various models. There is one that goes under the name of the acronym of IYIT for the authors that I don't have pronouncing now because I might get them wrong. But please look at the literature for the original paper. So it's all in the list of references that I So let's see how this one works. For instance, a very nice example for this one is the following: take a gauge group. I will not give you all the details because the details involve some nice but messy good theory. But for those of you who like good theory, and why shouldn't you? This is a very nice exercise. So let me tell you the broad line of this thing. So you take an SU5 gauge theory. You take two families of metal fields. One we call it Q tilde, and one we call it T. They're not Q and Q tilde. They are not vector-like. They are chiral. So Q is in the 5 bar, the anti-fundamental of SU5, and T is in the symmetric of SU5. Symmetric of SU5 is in the anti-symmetric of SU5. So the anti-symmetric of SU5 is in the 10. So this is in the this is the fundamental bar, and this is the anti-symmetric of SU5. There are two families. So I put an index here. I call them excuse me. I call them, I don't know what to call them. I didn't call them. F. 1 and 2. These are neither gauge indexes. These are not gauge indices. These are Freiburg indices. So for each F, this guy is in a 10 of SU5. For each F, this guy is in a 5 bar of SU5. Okay. Little check of what are the global symmetries of this theory. The global symmetries of this theory, remember, for every superfield in a presentation, if there are n f of them, and in this case there are 2, you always get an SU and F. So you're going to get an SU2 twiddle, which is the Flavor symmetry for the Qs. You're going to get an SU2, well, let's call it SU2Q. You get an SU2T, which is the Flavor symmetry for T. And then you get, how many U1s do you get? How many anomaly-free U1s are you going to get in this case? Can anybody tell me? So, classically, so forget anomalies. Forget anomalies. I can always rotate, sorry, I should have said. Start off with superpotential, sorry. 3-level superpotential, 0. Start off like that. So we have the full symmetry of the theory. The superpotential may actually break some of the supersymmetry. It will come back. The superpotential will be set not to 0 at some point, but not now. Take it to be 0. So all you see is what you get. So you can always rotate Q by a phase, or rotate T by a phase. So you always have you have a U1 for every family of Qs, and a U1 for every T. So you have 2 U1s, and then there is always our symmetry. So you have 3 U1s. But one linear combination of these 3 U1s would be anomalous. There is one simple gauge group, so the number of 3 U1s is the number of irreducible representation plus the R symmetry minus the number of simple groups or simple factors in the group. Right here, there's only one. So you're going to get at the end of the day 2 U1s that are anomaly free. One is the and you can play with the charges and see what they do. And one is some axial. It's all axial because there is no value number. This theory is scalar. And the other, let's call it R because this is the one that rotates the Griguolo as well. Okay, and it's a nice. So these ones are of course. It's a nice exercise in anomaly cancellation to check, and I hope I'm writing the right numbers here a bit quickly, but it's in the literature. In fact, it's one of your homework is this. I believe one of your homework is actually to do this and try to generalize this for SU5 and check that in fact the anomalies, you have to change the method field as well and check this thing. But this is the table that you get. These are the anomaly free, these are the ones that do not pick up an ABJ type of anomaly. Okay, so this is a statement that you can check by checking the anomaly. And then the other statement is that group theory in this case remarkably singles out, and these are not going to prove, but it's just basic group theory. Claim there is only one invariant G, so SU5 invariant, gauge invariant. Also invariant under all the flavor symmetries that are not R symmetries. Oops. And I want to construct, I'm doing this because I want to construct a superpotential. So you construct an object that has to be invariant, and it has to be gauge invariant, and it has to preserve flavor. Remember, this is the same game that we played in Super QCD, and has R symmetry equal to 2, because I want it to be in the superpotential. In other words, the superpotential is just like we did in Super QCD. When NF was less than NC, we went and looked if it was possible to generate a superpotential by looking if there was a possibility at all of generating something that could appear. And then we didn't know if it appeared or not. We had to do an instanton calculation. But if it could appear, it had to be that. It had to have that form. You do exactly the same thing here, but the group theory is a little bit more subtle because this theory is scalar. But you see that there's only one such term, and I write it down in its full glory. is equal to some constant that you're not allowed to fix by group theory. And sure enough, it looks just like the super QCD. It has the things are at the denominators. It has 2 powers of Q tildes and 6 powers of T. So it's a ridiculous term, but it's the only one that appears. So now you have to contract these things in a way, and I will not. So there are 2 epsilon tensors that allow you to make an SU5 invariant. So there is a group theory invariant of this type that I will not write down in its full glory, that has all of these properties. And this is the only one that has all those properties. All you got to do is to put lambda, remember, to the appropriate power to get dimension 3. Now, to get dimension 3, 1, 2, 3, 4, 5, 6, 7, 8, there are 8 fields here. I have to get dimension 3, so I have to put 11 powers of lambda. So this is the only term that can appear. 11 is another magic number, because what is the beta function for this theory? The coefficient of the beta function, the one good coefficient for the beta function of this theory. Remember, the coefficient for the beta function is 3 times the index of SU5, which is 5, minus 2 times the number of minus 2 times the index, 2 because there are 2 of them, times the index of the fundamental, which is 1/2, minus 2, because there are 2 t's, times the index of the antisymmetric, which is 3/2. And this is 11. Q. This 11 is the same as this 11, so I can write this as beta 1. So that means that these are the kind of non-perturbative correction. These are essentially the only kind of non-perturbative correction that we really know how to compute. And they're done by instant calculation. So if you see something that has the lambda to the appropriate power of beta, to the appropriate power, which is beta 1, then you know that if this term is generated, it will be generated by instant. So you can actually do an instant calculation, soaking up all the zero modes and so on, and you show that this is not zero. This is not zero. Then you have yourself a runaway. Now you have yourself a runaway system. So this theory now seems bad now, because we have generated an non-perturbative superpotential. So far, we are exactly in the same situation as massless super QCD with an F less than NC. This is obviously is a runaway potential. So have we done anything good? Not yet, but we can fix it very simple. Now add to this. Now add a 3-level superpotential lambda TAB, say 1 for the first family, first label, Q tilde. Let's take a gauge invariant. So A and B are the SU5 indices. I make them to be a gauge invariant object like that. And this is 1, 2, this is the family index antisymmetrized. So clearly this thing breaks the T1 symmetry, the SU2T symmetry, because it singles out one of them. But again, we play exactly the same game that we did all over the place. We think of this lambda now as a coupling, not as a coupling constant, but as the Viking expectation value of a superfield. So we say that this is alpha, and this is alpha. We give lambda the appropriate opposite rotations under SU2, and so this object here, by thinking of this as the Viking expectation value of a kind of superfield, is indeed invariant under all of the symmetries. So I can just pick one lambda, so I can just go back to the same lambda, and I can argue that the full superpotential is nothing but the sum of this term, which is non-perturbatively generated, plus this term that I put in by hand. Now, the difference between, this is exactly, let me write it down here, and then I'm stopping in 1 minute. So this is for this model. For the super QCD, we had a very similar situation. We had, say, super QCD with NF equal to NC minus 1. We had a very similar situation. Remember, we had the determinant of QQ tilde and lambda to the appropriate power, which was 2nc is the beta function, not maybe actually 2nc plus 1, I guess it was, if I remember right. Don't quote me on that, I don't want to do it right now. And so this was making it run away, right? But then we added, so without the three-level superpotential, these are two theories that are kind of not that good because they don't have a vacuum. They both run away. The fields, the potential can be made arbitrarily small if you go away to infinity in field space. But here we could stabilize this, of course, by adding a mass term. Now the potential is not run away anymore because if you go way out to infinity, you pay a lot of money here. When you look for the F terms, we did look for the F terms here, and the F terms here were actually SUSY preserving. So the potential for super QCD was something like that. When you put in the mass term, was something like this. And there was a zero, which we actually worked out, if I remember right, which was telling us the vacuum expectation value of this meson field. There is a value here that is SUSY preserving. Again, this is an example of the Witten index changing when you pull this m to 0. Because when you pull this m to 0, this thing goes off to infinity and the vacuum disappears. Now, this is exactly the same situation that we have here, only now the theory is chiral, so you have a different metal content. This is not a mass term, but this is actually a cubic term. You cannot write a mass term for this object because they're chiral. Now, you do the same calculation. It's a little bit tricky. It's a little bit of good theory galore, but you find, in fact, a very similar situation for this model. The only difference here is that you don't go down to 0. There is a gap. This gap means that this is a truly stable supersymmetric breaking vacuum, dynamically. So this is a SUSY breaking vacuum, dynamically generated by the one instanton computation that we haven't done. That you need by the interplane of this three-level term and this thing. If you were to throw the three-level away, then this thing would be, for the three-level, throwing away the three-level, this would become another way. Okay? So this was one of the first, if not the first example of dynamical supersymmetry breaking. Supersymmetry breaking generated, forced upon you by quantum collections. I do not have time to discuss the other case, which is this Y model, which is also cute. We can, if you're interested. By now the sky's the limit. Now there are lots of models. And phenomenologically, none of these things is terribly successful. There are problems. In fact, people are starting to wonder whether the truly phenomenological models of supersymmetry breaking are actually require essentially metastable states. It's a whole long discussion that I do not have time to do in this -5 minutes that I'm left with. So I conclude. I thank you very much for listening to me. It has been a pleasure, and I wish you all the best for the future. Okay.